Yeah. In this session, let's look at this central limit theorem, which is actually a kind of a bridge between the probability world and the statistics world. And it has a lot of applications in inferential statistics. Especially, it has brought in a lot of concepts into the world of inferential statistics because of a big assumption that has come, or a big conclusion that has come in terms of the pattern in the data, especially when you want to compare the means of a population. The mean of a population, if you want to make some kind of conclusions or inferences regarding the mean of a population, we are resorting to the central limit theorem. What it is saying is, see, if especially if we are working with sample of data and we want to make some kind of inference about the population, like the mean of a population, we want to compare the mean of a population with something, or we want to say whether the average height of males is greater than the average height of females. Whenever we want to make such kind of conclusions in statistics, because any statistical calculation which we have to do, apart from calculation, there is an inference or a conclusion angle associated with it. And to make those conclusions more and more comfortable, the central limit theorem is really helping us out with. What it is saying is, if you look at the various random variables, x1, x2, x3, if you are thinking of the various random variables, which are nothing but, let's say you are talking about a data. Like, let me just show it to you. I'm taking a data. Let's say this is, I'm taking some values randomly between 51 to 200. Some numbers I'm taking randomly. So let's assume there is a data whose values are lying between 51 to 200. Now what I'm doing, I'm taking a sample. Let's assume I have taken 100 items, out of that some population, or probably let's talk about the heights of people. Randomly I am assuming that the heights of the people are between, let's say, 140 centimeters to 200 centimeters. Any person I am taking at random, his height would be somewhere in that region. So like that, what I am doing, some 100 people's height, on a random basis, I have picked up some people and I have measured their heights, right? And I have taken their average. I don't know what the distribution the data is. The data can be either a normal distribution or a uniform distribution or whatever it is. What I will do is, out of that entire population, I have taken a sample of size some 100 people, and let's say I am measuring their average height. Now, what is their average height? Let's say I got here 170.73. Okay, I will note down all these sample heights, 170.73. Then another random sample, some other sample came out, and for that sample the average came out as 169.37. Another 169.21, like that, 171.08, like that I am getting various averages, right? 169.37. So it's like you are randomly selecting some 100 people, right? Some 100 people you are randomly selecting and you are measuring their average height. right? In some cases, the number is much lesser. In some cases, the number is much higher, right? Like this, you can repeat so many times. You can take some 100 people and measure their heights. And this is how you can document all their height, all their average heights. We are not documenting their heights, we are documenting the average. Correct? Now, what the central limit theorem is saying is, when you take a sample of some size n and you look at their sample mean, this is their sample mean, these are their sample means, sample average. What it says is the sample mean also keeps changing because your sample is changing. The sample mean is also changing. But what they say is this sample mean actually follows a normal distribution. This sample mean, because it is changing, first of all, it's a random variable, not the data. I'm talking about the mean itself. The mean itself is a random variable because it is changing. And what the central limit theorem has come out is, this sample means they follow a normal distribution. Whatever is the distribution of this data, doesn't matter. The sample means will follow a normal distribution with the mean. Now, if you just want to check out, I can look at the skewness in this. Skewness should be 0 for a normal distribution. Okay, I'll check out for the skewness. It will be very close to 0 itself. Probably if I take a few more like this, we may find that the skewness will be very close to 0, which is an indication of normal distribution itself. So what it says is, in case of a normal distribution, in case of any distribution, when I look at the sample means will follow a normal distribution with a mean. Now, what is the mean of this? The mean of this is something. The mean of this will approach the population mean. The whole population, whatever we are talking of, it will be more equal to that population. It will approach that population mean with a variance equal to sigma squared by n. Sigma squared is, from here I can take the standard deviation squared, or the variance I can take, or standard deviation is sigma by root n. So I'll take a standard deviation of this, so 18 or something, by root n. Root n is root 100. 100 is our sample size which we have taken in this case. So I will take it as root 100. Now what it says is, when I go with it, the sample mean, these are all the sample means. The sample mean will approach the population mean with a variance of sigma squared by n, or with a standard deviation of sigma by root n. Which means this one. 100 sample of size 100. It's like the heights of 100 different people on a random basis. So you may pick this 100 set of people. I may pick this 100 set of people. From the population is same. Population could be some 1 lakh people. Out of that I am pulling out some 100 people. So the actual members will be different. The actual members of that will be different, but the size will be the same. See, why we are thinking of this? Using the sample, we want to make some prediction about the population. See, basically, I don't want to go to 1 lakh people and measure their heights. Right? So, I am just trying out some 100 people and measuring their heights. I got some number. But that may not be the same of 1 lakh. The average height of the some 100 people may or may not reflect the 1 lakh people. So what we are saying is, probably you do one more 100. You do one more 100. You do one more 100. Now, if every one of us do 100, again there is a big cost to it. Now, what the central limit theorem has come out with is, if so many of you are doing some 100 samples kind of stuff and measuring the averages, each one will get a different number. Like you got 170, I got 169, someone else got 169.21. These are the averages. Now, without doing all this, what it is saying is, you do it only for one sample. Probably for one sample you do it. You do it for one sample, and so your population average will be something similar to your sample average plus or minus some interval around it. Right? It's basically, if you see here, the averages are more or less in a small region. Even if all of us are taking different 100 people, the averages are in a small region only. They are not widely varying. So that is what central limit theorem could prove, saying even if you do it with one sample, right, you build an interval around that sample. So the population mean will be same as the sample mean plus or minus something. So the population mean will lie in I am able to predict an interval for the population mean, not a pointed value. In most of my prediction, we do an interval prediction for the population mean, not a pointed prediction. Because see, it's like this. You want to measure the average height of Indian male in general, right? If I have to measure it accurately to a point, this is the average height. We have to measure the heights of each and every person. But that could be a very big costly exercise. I have to engage so many people to measure the heights. Now, rather than that, what we are saying is, if I do it with a sample, if I measure the heights of some 100 people, I will get some value. And what the central limit theorem is bringing out is, take that sample's average only and build a small interval around it. That interval, what it is saying is, the interval can be built because they are saying that this averages, the sample averages, they follow a normal distribution with a standard deviation equal to sigma by root n. Sigma is of this population. Root n is whatever is the sample size you have taken. You have taken a sample of size 100. So whatever is the sample size you have taken. So basically it's like this. If you have taken 170, for one sample, if you have got 173 and the standard deviation by root n, which you have got as 1.9. Now what it is saying is, around 173, you build a small interval. You build a small interval using that number 1.9. Getting it? So you don't need to really predict the whole population's average. Even if you are predicting the population average, you are not talking about a one dotted point for the population average. You are giving a small range. You will say that the Indian male, the average height of an Indian male is somewhere between 165 to 175, which is a decent way to predict, rather than saying 169.23. Right? That is what a central limit theorem is able to bring out. saying at least you can, just by taking one sample of observation, one set of sample, you can very well do the prediction for the population mean in an effective manner. So instead of me trying out all these things, even with one sample, whatever the value that I have got, I can build a small interval around that sample and say I am 95% confident that the population mean will lie between this and this. Or I can say I am 99% confident that my population mean will lie between this and this. So which means there is only 1% chance of the population mean outside that interval. Even that is sufficient for a statistician to majorly compare, let's say, two data sets. Is the average height of an Indian male more than that of an American male? For those kind of conclusions, it can really help us. I'm not bothered about what is the exact number, right? I want to more talk about, even if it is in a small range, is it a confident kind of a range? How confidently I can say that the predicted value is within this particular range? So that is what is being brought about by our central limit theorem. So what is, and in this case, what it says is, let the sample size be large. If I don't know the distribution of the original data, see this data, I don't know what distribution it is, right? It could be anything, but this will follow normal only. That is what the central limit theorem is saying. This could be a uniform distribution, log normal, whatever it is. But this will typically follow a normal distribution itself, right? So if the distribution of this data is not known, or if it is not normal, even if it is known, but if it is not normal, at least a sample size of 30 plus is required. 30, 40, 50, a sample size not of 5 or 10, at least 30 plus is required. But if this is a normal, even 10 is also sufficient for us. If this is not normal, a slightly larger sample size is required. That is what he is saying. If the distribution is more skewed and is not normal, even a 50 is also fine. 30, 40, 50 kind of stuff. But if it is normal, then even a 10 is also sufficient for us as a sample size. Right? That it will still follow a normal distribution. Okay, now what are we saying here? One of the numericals, let's say we look at the number of claims that arriving at an insurance company per working day has a mean of 40. Standard deviation is 12. This numbers. In this, we are trying out that the mean is 40 for some of the sample which we have taken. The standard deviation is 12. A survey is conducted over 50 working days, like that which we have taken out. So 50 working days is what we are talking of. So which means n is 50. The sample size which we are taking is 50. For each day, we have collected the number of claims. Just like this you can think of. For each day, we have collected the number of claims. For 50 days like this. For 50 days, we have number of claims collected. The mean is 40. The standard deviation is 12. What it is saying, calculate the probability that the sample mean of the number of claims arriving per working day was less than 35. Now we know that this will follow a normal distribution. What is that normal distribution? The mean for that normal distribution will be 40. Right? For the sample mean, the mean will be 40. Plus, what is the deviation around that? Sigma by root n is the deviation. Sigma by root n in our case is 12 by square root of 50. The standard deviation. Okay, the standard deviation of the sample mean is 12 by square root of 50. This is the standard deviation of the sample means 1.69. So the mean is 40. The sample, the population mean will be same as my sample mean, will lie in an interval for the sample mean. Sample mean plus or minus something based on the standard deviation. And the good things about a normal distribution is 95% of the data lies between plus or minus 1.96 standard deviations from the mean. There are some of the aspects associated with a normal distribution. When we are talking about any normal distribution, if this is the mean, and let's say this is 1.96 and minus 1.96 standard deviations from the mean, between those two I will see 95% of the data. And similarly 99% of the data, these are all very common kind of aspects. 99% of the data lies between plus or minus 2.58 standard deviations from the mean, and so on. But for us, from a calculation standpoint, I have to find out what is the probability that the average claim is less than 35 in a particular day. Average number of claims arriving in a working day is less than 35. So for that, what we can do, I can very well convert this into a standard normal distribution. So how x minus 40, so every value I subtract the mean and divide it by its standard deviation. The standard deviation for us, we got it as 1.69. For the mean, the standard deviation is always sigma by root n. For the data, it is sigma, but for the mean, it is always sigma by root n. So 1.697. So we want the probability that x minus 40 by 1.697 is less than 35 minus 40 by 1.697. So this is nothing but a standard normal distribution, z less than 35 minus 40 by 1.697, which will work out as 35 minus 40 divided by 1.697, working out to minus 2.94. What is the probability that z is less than minus 2.94? I can look out in the normal distribution tables, right? When I am looking out in the normal distribution tables, z is less than minus 2.94, it comes out that 0.001. So which is 0.16%. 0.16% chance that the claims on any one single working day will be, the average number of claims in a single per working day will be less than 35. The probability is only 0.16%. Right? So using the central limit theorem, we can actually do a good prediction of the average number. What is the chance that the average number of claims less than this, average number of claims more than this, or average number of claims lying between this and this? So it's a good tool to do the prediction of the averages of the population based on one single sample of data. So probably in this context, you can use the central limit theorem more and more effectively. If the objective is to find out the population mean, in what range will it lie, or the population mean less than or equal to something, greater than something, what is the probability associated with that? If these are the kind of things we have to calculate, we can very well use the central limit theorem. Now, the common applications are, in most of the cases, we see that the binomial theorem or binomial distribution, we can approach it to a normal distribution. The Poisson distribution, we can approach it to normal distribution. Almost every distribution, we can very well approach it to a normal distribution itself. But the most common applications being the binomial and Poisson. Lot of applications, especially if n is large in binomial, if the number of experiments are repeated many number of times and the probability of success or failure are very small, one of them is very small, then what we are saying is the binomial I can very well approximate it to a normal distribution. See, we know that the mean of the binomial distribution is NP. The variance is NP into 1 minus P. Even for the normal distribution, I will take the mean is NP. If I want to use normal distribution for a binomial distributed data, right, the question is given as binomial distribution. But because NP is greater than 5, in this case I can actually use the binomial normal approximation. NP is greater than 5 or even n into 1 minus P is also greater than 5. If both these are greater than 5, I can think of using a normal distribution approximation to a binomial distribution. In this, what I am doing is whatever are the mean and the variance of the binomial distribution, I will use them as the normal distribution itself, as the mean and the variance of the normal distribution itself. And I will use them to solve the numerical problems. The same logic goes with a Poisson distribution also. Even in a Poisson distribution, I will look at lambda, which is because in a Poisson distribution, the only parameter is lambda. The mean and the variance, both of them are equal to lambda itself in a Poisson distribution. So, if lambda is greater than 5 in any question, if lambda is greater than 5, I can think of the normal distribution approximation to the Poisson distribution. So, in that case also the normal distribution will have a mean of lambda, the variance of lambda. So, basically what we are saying is even if a question that comes to us is on a binomial or a Poisson distribution, right, even if it is based on a binomial or a Poisson distribution, we can very well convert it into a normal distribution. We can take the equivalent of a normal distribution, especially if NP is greater than 5 and in n into 1 minus P is greater than 5 in case of binomial distribution, and lambda is greater than 5 in case of Poisson distribution. So basically our discrete distributions of binomial and Poisson, they are getting converted into a continuous distribution like normal. So in most of the questions, we'll see a couple of questions also. In most of the questions, if this kind of criteria is met, instead of using the binomial distribution to find out the probabilities, people look at using the normal approximation itself to find out the probability. The same logic can be applied even to other continuous distributions also, like gamma distribution and all. Right? At the end, whatever is the mean and the variance of those distributions, right? For a gamma distribution, the mean was n by lambda and the variance was n by lambda square, or k by lambda square, alpha by lambda square. We generally, the most common thing which we use is alpha by lambda square, are the mean and variance of the gamma distribution. Now, all I can also do is, normal approximation is nothing but take that mean, take that variance and put it into a normal distribution. But the biggest thing is, because gamma distribution is a very highly skewed kind of a distribution, you find it positively skewed. So because of that, when I do a normal approximation, the results are much poorer compared to actually doing a gamma distribution only and then doing the predictions. Compared to that, If I am using a normal approximation of a gamma distribution, the results are not that successful. So basically heavily used only for binomial and Poisson kind of distribution, but you don't use them for gamma and other kind of distribution, right? And the basic advantage is using a normal distribution. There are a lot of advantages, right? Probably I can use the normal distribution tables to find out the probability, and lot of things like 95% of the values lie between plus or minus 1.96 standard deviation. So building the intervals for a prediction purpose becomes more and more easier the more I can approximate any distribution to a normal distribution. Lots and lots of applications have been developed, like correlations, regressions. Lot of statistical applications have been developed under the assumption that my data is following a normal distribution. If the data is not following a normal distribution, probably if I can do this kind of approximations to normal distribution, still I can use the data for my analysis purpose more effectively itself. Now we'll take in this, there is a small thing that we have to take care of while using the binomial and Poisson for converting them into normal. One thing is binomial and Poisson are discrete distributions, whereas normal is continuous. So basically it's like in case of binomial or Poisson, you will have something like, okay, what is the probability that x equal to 1? What is the probability that x equal to 2? Probability of x equal to 3. But you may not have things like what is the probability of x equal to 1.23, because not all values are possible in case of binomial and Poisson. So you will have only some discrete finite set of values there. But in continuous, that's not the case. Almost every value is possible. So what it is saying is, whenever we are talking of a conversion from binomial to normal or conversion from Poisson to normal, do what is called as a continuity correction. The way they are talking of continuity correction is something like this. Whenever I am saying x equal to 4 in a binomial, whenever I want to test out what is the probability that x equal to 4 in a binomial distribution, what it goes as a Poisson when I convert it into normal, because normal distribution is a continuous distribution and it exists only for a range. It does not exist for a value, right? So what it says is, you find out the probability of 3.5 less than or equal to x less than or equal to 4.5 or less than. 3.5 less than x less than 4.5 is, so basically it's like the rounding off of 4. When you want to find out x equal to 4, take the interval as 3.5 to 4.5, because in a typical rounding up also, anything which is 3.5 above, we round it up to 4. Anything below 4.5 also, we round it up to 4. So what it is saying is, if you are converting a binomial to a normal, if wherever the question is talking about find the probability of x equal to 4, in the normal distribution case, find it as the probability of x lying between 3.5 to 4.5. Similarly, if the question talks about find the probability of x greater than 4, right? In a binomial case, what is x greater than 4? 5, 6, 7, they are the ones. So when you are taking it in normal case, you take it as greater than 4.5, because 5 means in a continuous case, anything greater than 4.5 will be taken as 5. So when you take it into normal, take it as x greater than 4.5. If the question says find x greater than or equal to 4, greater than or equal to 4 means even 4 is also included in the binomial. So 4 is also included means you have to start from 3.5. Right? So depending on what is the question that is asked in the discrete, you will make the appropriate correction in the continuous case. That is what we are calling as the continuity correction. So if we look at some of the numericals, it becomes easier for us to solve the questions in this chapter. The average number of calls received per hour by an insurance company switchboard is 5. So lambda is 5. Calculate the probability that in a working day of 8 hours, so this is per hour. Per hour is 5. Calculate the probability in a working day of 8 hours, the number of telephone calls received will be exactly 40. So I can very well take lambda equal to 40 for 8 hours. Per hour is 5. So for 8 hours I can take it as 40. Now what is the question is saying? Exactly 36. So if I take probability of x equal to 36, when I am taking it into normal, see, okay, let's take it in both the ways. I will compute the exact probability using the Poisson distribution and probably converting it into normal, approximating it to normal, and we'll try to find out the probability. So if we are using directly the binomial, directly the Poisson itself, lambda equal to 36 here, sorry, lambda equal to 40, I want a probability of x equal to 36, right? E power minus lambda into lambda power x by x factorial. Okay, e power minus lambda into lambda power x by x factorial. Sometimes these calculations in calculators become very, very difficult also. These numbers, the rounding offs and all these things come out. So, okay, anyhow, it has given that the probability is around 5.39%. There is a 5.39% chance that the number of calls, average number of calls during a day is exactly equal to 36. If I do a normal approximation to the same, see, even in calculator, factorial 36 or probably the 40 power something, 40 power 36, they are all very difficult to calculate, right? So, okay, now what we are saying is, let me approximate the Poisson to a normal. So, if I am approximating the Poisson to a normal, what should I do? The question is about equal to 36. So, which means I will try to find out 35.5 less than x less than 36.5. Now, so if I am talking about 30, so here because it is Poisson, my mean is 40, variance is also 40. Lambda is the mean, lambda is the variance for the Poisson. So for the normal also I will take the same. Mean equal to 40, variance equal to 40. Variance equal to 40 means the standard deviation is square root of 40. Right? Square root of 40. The standard deviation is somewhere around 6.32. So the question is asking about 35.5 to 36.5. So which means in a normal distribution, I want to find out some area which is lying between this 35.5, 36.5. I want to find out what is this area. Right? So for 35.5, what is the standard normal value? I can take it as 35.5 minus 40 divided by the standard distribution, standard deviation, which is minus 0.71. The same logic I can apply 36.5 minus 40 divided by the standard deviation. So minus 0.55 to minus 0.71. I will find out the normal distribution values for these two things x less than minus 35, minus 35.5, I will take x less than minus 36.5. I subtract the one from the other, it will give me lying between 35.5 to 36.5, right? So I'll take the normal distribution values corresponding to both of them. So for this, it is around 0.23 is the area. From the tables, this is what is coming out. And for this, the area is around 0.28. I subtract one from the other, I will get that the probability is 0.051. Even when we have done it in the original Poisson distribution route, we got that the probability is 5.39%, right? Even when we have approximated the Poisson to a normal, we got the probability as almost 5.16. There is a small difference existing, but sometimes it becomes difficult for us to calculate using the Poisson. Whereas when I have approximated it to normal, things become more easier to calculate. That's one of the prime reasons people use the approximations to the normal, because anyhow the answer will not be that widely deviating. So you can very well make your calculations more and more appropriately with not too much of an effort. Now, the same logic between 42 and 45 inclusive. So when you are taking it into the Poisson, what are the things that you, I mean, when you are doing it in this is where the advantage comes for you. In your Poisson, how do I find out 42 to 40? When you say between 42 to 45 inclusive, you have to find out probability of x equal to 42, 43, 44, 45. You have to find out 4 of them and you then add up, right? So probability of x equal to 42. So you are saying e power minus 40 into lambda power x 40 power 42 divided by 42 factorial. Like this, what is happening is, especially if this kind of question is there, it becomes a much big exercise. Right now the same thing I have to do for 43, 44, 45, all these. I have to do for 43. Now here at least there are only 3 or 4. Right, but in some case, and that too when you imagine that you are doing it with a calculator, not with a spreadsheet, it becomes even more a painful exercise. You do all that and you have to add up all that. That's a big pain. Now what, so in this case, anyhow the answer comes out probably to around 20%, looks like close to 20%, around 20.63%. Now what we are saying, for this, I can do it as approximation to normal. What is that I have to do when I have to do an because I am talking of inclusive of 42 and 45. I will take the range as, because 42 also need to be included, I will start from 41.5 less than x less than, because 45 also need to be included, I will take 45.5. Now when I take the normal, so I will convert both of them into standard normal. So 41.5 minus 40 divided by the standard deviation, which is 6.32. So I want to find out what is the area corresponding to 0.23. Even this also I will convert it into standard normal. 45.5 minus 40 divided by the standard error, standard deviation, 0.86. Now from the tables I will look out for 0.23. So what is the area I will get corresponding to 0.23? The area that I am getting is 0.59. From the left to that it is 0.59. We have discussed about how do I look out in the normal distribution tables. Now the same logic here, it comes out to 0.80. I have to take the difference between these two areas, because I want, this is like Less than 41.5, it is 59.37%. Less than 45.5, it is 80.77%. I want lying between 41.5 to 45.5. So I have to take the difference between the two areas. So when I take the difference between the two areas, I am getting it as around 21.4%. Even when we have done that mechanism, so we don't need always the exact numbers. See, anyhow, because this is an approximation, we'll find it small differences will definitely exist because it's not a proper normal distribution. We'll always see small differences existing. But what we want is on a broad scale, on a high level scale, what is the typical typical probability that a value lies between this and this. And imagine, especially instead of just 4, I want to find out what is the probability that the number of calls are between 40 and 50. Doing it through Poisson, doing it through binomial is actually a very painful exercise. Right? For so many things I have to find out, it becomes a very painful exercise, and that is where again central limit theorem has brought in our advantage. You can do an approximation of these binomial or Poisson distributions to a normal distribution, and you can very well use them for the solving purpose. Right? Okay, let's look at some of the questions here. Use a normal approximation to calculate the approximate value for the probability that an observation from a gamma 25, 50. So alpha is 25, lambda is 50, falls between 0.4 and 0.8. So again, for a normal, I will make it like the mean is the mean of the gamma itself, alpha by lambda, which is 0.5. So I will take this 0.5 as the mean of the normal distribution. What is the variance of the normal distribution? Whatever is the variance of the gamma distribution. 25 by 50 into 50. Probably 1 by 100 or 0.01 is the variance. The standard deviation will be the square root of 0.01, which is 0.1. For the normal distribution, my mean will be 0.5. The standard deviation will be 0.1. Now, based on that, I can find out what is the probability that a random variable will fall between 0.4 and 0.8. Right? The same, convert it into a standard normal. Right? Equal to 0.4 minus 0.5. The mean is 0.5 by the standard deviation is 0.1. And the same one, the second, 0.8 minus 0.45 divided by 0.1. Things are very simple for us the moment we can take it into a normal distribution. Again, I'll look out for these two values. Right? So the normal is the table value for this is this much, and the table value for this is this much. The difference between the two, if I am taking, it is telling me that around 84%. The probability that the value will lie between 0.4 to 0.8, it is 84%. Without doing too much of gamma and trying to find out all those things, at least we can do an approximation. So it will not be exactly equal, but to a large extent we can bring the approximation in a much better manner. So from any distribution we can think of the same. What is the approximate probability that the mean of sample of 10 observations from a beta 10-10 distribution falls between 0.48 and 0.52. Again, from a beta distribution, I should be able to find out what is the mean, what is the variance. For a beta distribution, again there is a formula for mean and a variance. Right? I can find out the mean and the variance for a beta distribution and associate that to a normal distribution. So basically any distribution can be approximated to a normal distribution. Simple logic is you find out the mean of that distribution you find out the variance of that distribution. For a beta distribution, what are the mean and the variance? Again, we have our formulas, right? Let's see what are those formulas. So I can very well take the mean of the beta distribution as alpha by alpha plus beta. So the mean of the beta distribution is 10 by 20. So 0.5 is the mean of the beta distribution. So the same thing I will take it to the normal distribution. Okay. Now we are also talking about the variance of the beta distribution, alpha beta, which is 10 into 10, 100, by alpha plus beta squared, 10 plus 10, 20 squared, 400, into alpha plus beta plus 1, 10 plus 10 plus 1, 21. So probably 100 by 400 into 21, 100 by 400 into 21 is the variance of the beta distribution. So what would be the standard deviation of that? I'll take the square root of this, and this will become the standard deviation of the beta distribution. Now the same can be translated to your normal distribution. But look at the question now. The mean of the sample. We are not asking about the sample. We are not talking about the sample distribution lying between this and this. Look at the difference between the previous question and the current question. In the previous question, the value itself lying between 0.4 to 0.8. Whereas here in the next question, it is talked about that the mean of the distribution lies between 0.48 and 0.52. Not the value lies between 0.48. So whenever the question is about mean, we have to find the standard deviation, not as just the standard deviation. We have to take it as sigma by root n. So when I am taking sigma by root n, here the sample size is 10. So I will use this as the standard deviation, not the original sigma. So now what I will do, 0.48 and 0.52. That is what he wants. So for 0.48, I will find out the standard normal distribution. 0.48 minus 0.5 was the mean, divided by the standard deviation. This is the one. And similarly 0.52. 0.52 minus 0.5 divided by this one. So the area wise, I can find out from the normal distribution tables. The area is 0.28 here, less than this much. And if I want less than 0.57, again I will get it as around 71%. So if I want to find between these two, I'll take this minus this. So there is a 43.78% chance that the sample mean for this beta distribution falls between 0.48 and 0.52. So even without too much of the integrations and all, right? If I have to do some kind of calculation on a beta distribution, obviously I may have to use the integrations and all that stuff. But by doing this normal approximation to all these distributions, at least to some extent, we are just by knowing the mean and the variance of those distributions, the same mean and the variance, we are carrying them into the normal distribution, and based on that we are able to find out the probabilities. So even if the questions come in terms of find out the mean and variance of the beta distribution or something, you can very well talk about approximating it to a normal distribution, and you can go ahead solving the question also, right? So the gamma we have seen, beta we have seen, almost any distribution, the moment you know the mean and the variance of that distribution, we can very well approximate it to a normal distribution and try to find out the probabilities of something lying between something and something. Fine. Now look at the next two. The probability of any given policy in a portfolio of term assurance policies is considered to be 0.15. For a group of 100 such policies, probability that more than 20 will lapse before they expire. Right? For a group of 20, we are talking, for a group of 100, we are saying what is the probability that at least 20 will expire. Again, the same, probably here I would have to use the binomial distribution in a normal case. 100 policies, each policy, the chance of expiring is 0.15, which means the chance of not expiring is 0.85, right? So basically it would have been like a probability of x greater than 20. It would have been a binomial distribution case where probably find out for 20, 21, 22, all those stuff, right? 20 will not be there, more than 20 will lapse. So from 21 to 100, you have to find out the probabilities. Or on the other side, at least find out from 0 to 20 and subtract 1 from it. Both are tedious process only if I am going with a binomial distribution. But if I do a normal approximation, I know the mean of the normal distribution is how much? NP. I'll take the mean of the binomial itself as the normal distribution mean. So the mean for the normal distribution is NP, which is 15. The variance is NP into 1 minus P, 15 into 0.85. The variance of the normal distribution, or which is the variance of binomial distribution, is 15 into 0.85, which works out to some 12.75. The standard deviation is coming out to the square root of this 0.75, which is standard deviation is coming out to the square root of this 12.75, 3.57. Now the question is find out x greater than 20. And because we are using binomial, we have to do a continuity correction. This is one place where people make a mistake. You start with 20 itself and he catches hold of that in the exam. If you are using the binomial, make sure that you are doing a continuity correction. So if the question is saying find the probability of x greater than 20, you start with 20.5. Right? So what you are doing, you find out the standard normal distribution corresponding to 20.5. 20.5 minus the mean is 15 divided by the standard deviation, which is this one, 1.54. So we will get in our tables, we get the value less than 1.54. But I want greater than 1.54 because this is, we are talking about x greater than 20. So I'll do a 1 minus of it. So I can find out the normal distribution table value corresponding to this 1.54, which gives me 0.93 something. So if I want to find out the 1 minus of that, it is around 6%. So there is a 6.17% chance that more than 20 policies will lapse. Obviously the average is 15, right? If more than 20 have to lapse, the chances are lesser itself. So the chances are coming out to only 6 point some percent that the more than 20 policies will lapse. So this is how we have to take the binomial distribution and approximation of the binomial distribution to the normal distribution. Now the same logic if we are going with a Poisson, number of claims arising in a month under a home insurance policy follows a Poisson distribution with mean equal to 0.075. So for a Poisson distribution, mean and the variance both are same. So these are some of the things we have to be comfortable with. Lambda equal to 0.075, though he has given a mean is 0.075, we have to say because it is Poisson, variance is also 0.075. So calculate the approximate probability that at least 50 claims in total arise in a month under a group of 500 independent such policies. So per policy we are talking of 0.075. So for 500 policies, my lambda is direct multiplication. 500 into 0.075 is my lambda for 500 policies. For 500 policies, my lambda is 37.5. So mean is also 37.5. Variance is also 37.5. So I take the square root of this, it becomes the standard deviation is 6.12. Now I have to find out at least 50 claims. So probability of x greater than or equal to 50. Greater than or equal to. So which means from our continuity correction standpoint, I have to find out greater than 49.5. Right? So when I am using the normal distribution, I want it as greater than 49.5. So when I take it into the normal distribution, 49.5 minus 37.5 divided by 6.12. I want that z value greater than 1.959. Right? So probably I'll find out for less than that first of all, and I'll do a 1 minus of that. So you have to be comfortable on where you should do that 1 minus and where you should keep it as it is and all, depending on, because the tables will only talk about the less than, that to a positive value. So it is coming out like 2.5%. There is a 2.5% chance that at least 50 claims will come out of the 500 independent claims. So in this chapter, the most important aspect is how a central limit theorem can be used for approximating a sample mean to a population mean, and along with that how you can actually build intervals, because once you know it's a normal distribution, we know a lot of things about the probabilities and all from the normal distribution tables, and that too how the discrete distributions like binomial and Poisson, or for that matter continuous distributions like gamma and beta can very well be approximated to normal, and any calculations on those things can be computed using the normal approximation to those. And in the coming up chapters, the most focus is building the intervals, doing the conclusions, inferences kind of stuff. So because of this central limit theorem, what is happening is, without using too much of integrations and all those things, right, we are, by doing some kind of approximations, we are able to handle the consequences of the normal distribution, take the advantage of the normal distribution and find out the probabilities and the inferences in a much more appropriate and effective manner.